with projective manifolds, which are similar to affine, but they sit inside complex projective space instead of affine, complex affine space. So complex projective space is a set of lines. Projective space is all lines, one-dimensional subspaces. So it's CP n. This is definition. Subspaces in Cn plus 1. You can consider this a homogeneous space if you know Lie groups. If you don't know, you shouldn't care. But I will define it as a manifold next slide. So no questions to that? So it has, if you have a point in non-zero point, so if you have x inside Cn plus 1 without 0, you write its coordinate as x0 dot x1, x2, and so on, xn plus xn. And the columns here denote that it is defined up to a multiplication by a scalar, in the sense that so this is, one of them is non-zero, and then this is equivalent to lambda x0 colon lambda xn. So this is this called homogeneous coordinates. This is, I mean, each point doesn't give you one set of numbers, but the whole line of numbers, denoted like that. And there is also affine coordinates, which are obtained coordinates. So you take CP, you take a subset, CP, like let's call it A K, for instance, inside CPn, containing the points x1, x0, colon, dot, xk, colon, dot, colon, xn, and xk is non-zero. This is a K affine coordinate patch, and then there is a unique. There exists a unique n tuple, n plus 1 tuple, in the same set. So you take an equivalence class under this equivalence relation, such that which is equal to x0 divided by xk, x1 divided by xk, and then you have 1 in the in place of this xk, and so on, and then xn divided by xk. Clearly, this is one-to-one correspondence between this set and this. So this gives you a affine coordinate system on this set, and then the transition functions are written there. So if you have two AK and AL, from AK to AL, it's just a scalar. Takes x0 divided by xk, and so on, xn divided by xk. And since this is an intersection, I mean a point, so it belongs to the intersection of AK with AL, then AL coordinate is non-zero as well, and it's mapped to a multiplication by a xk to xl. It's mapped to a x0 divided by xl, and so on, xn divided by xl. So here you have 1 on the place number k, and here you have 1 on the place number l. Okay, this map is clearly differentiable, so this gives you a structure of differentiable manifold. In fact, it's a complex manifold because this map is also complex differentiable. Yeah? Good. Now I'm going to give you something that you probably know. So there's a theorem. Suppose you have A1 dot AN operators in complex space, in complex vector space. Then there exists commuting. Then there exists a common eigenvalue, common eigenvector. Who of you already knew that? Okay, the argument is quite clear. Proof. Okay, let's start with 2. So you have A1 and and A1 and A2 commute. Since we work over C, there is a non-trivial eigenvector and eigenvalue. Let's call eigenvalue alpha is eigenvalue of A1. And V, so I would denote this space by V. V is Cn. V alpha is eigenspace of A1 with eigenvalue alpha. Eigenvalue alpha. Then you have A2, A1, and V is inside this space. A2, A1 of V. This is the same, of course, as A1, A2 of V. On the other hand, this A1 of V is alpha V, so this is the same as alpha A2 of V. You see, A1 A2 of V is same as alpha A1 of A2 of V. Then this means that A2 preserves V alpha. And then this means that it has eigenvalue, has eigenvector. Okay. Then you take A3, you act by A3 on a common eigenspace of A1 and A2. You again notice that A3 preserves this eigenspace. Then it has an eigenvector, which would be common eigenvector of A1, A2, and A3, and then use induction. I wrote on the slides slightly different, but I think the argument is the same. This is very standard linear algebra. In fact, it was in my handouts. Shall we go on? Questions, comments? Okay. And then this was again in the handouts. We have this theorem about representation of finite commutative groups. It's a theorem. If you have V complex representation of G, which is finite commutative. Then V is direct sum of Vi, where Vi are one-dimensional representations of G. So the proof is very easy. All these elements commute, right, in the group. This means that they have common eigenvector, which gives you a one-dimensional space. So by this lemma, which I just proved, it's theorem here. Theorem. Let's rename it to lemma for consistency. By lemma, there exists one-dimensional subspace, W inside V, which is, it's preserved by G, so it's G invariant. Okay, and then we did do the same as we did last time. Well, every time when we did work with the representation of finite groups, we'll introduce Hermitian form, which is invariant under the group. For that, we take any Hermitian form and average it with respect to the group. Then V is W plus V W orthogonal, where orthogonal is taken with respect to G invariant Hermitian form. Okay, this is also a representation because it's orthogonal to something, to a representation. It's a representation, but using induction, we can assume that W orthogonal is direct sum of one-dimensional representations. This finishes the proof. So I'm going to prove you the same result for C infinity. Oh, sorry, C star. So same is true for C star. Not quite true, because if you consider C star as an abstract group, it is a product of like roots of unity and free groups. Free abelian groups, and we don't like these abelian groups because free abelian group, it doesn't have this property. But this is something we had in some of handouts. There's an abelian group, Z, which has no non-irreducible representation, non-semi-simple representation. But so for this is actually why C star is different from C. C star doesn't have, but we should do something, say something about representations. What I will ask is that representation algebraic, which is very natural because we work on algebraic geometry. So let's define algebraic group. We don't want to work with C star as abstract group. It's a very bad abstract group. But as algebraic group, it's a very good group with very nice representations. Okay, so definition, algebraic group. So you have affine variety equipped to the group action. Let G be affine variety equipped with group structure. Group structure is a map mu from G times G to G, and inverse iota from G to G. This is inverse. And this is multiplication. Such that mu and iota are morphisms of algebraic maps, morphisms of algebraic varieties. This means that they're represented by polynomial maps in the coordinates provided by Cn. Then G is called algebraic group. Let me give you immediately an example, which would be essentially the only example where going to work with. But in fact, there's lots of work in algebraic groups. I mean, it's part of V theory, but there are lots of works on it, and especially on exotic fields, not over C, but over R, or even more strange fields like algebraic closure of finite field or something. It becomes highly non-trivial. Even the Lie group theory, which is completely clear over C, becomes non-trivial. It has lots of open questions if you work over other fields. This definition works in fact, it works even over Z. So you don't, if you speak of affine varieties divided by polynomials, not in Cn, but it's doable. Anyway, so let me give an example. I will take C star, which is C without 0. And it has, first it has coordinates. This is a affine variety. This is something that we have because this is C star is the set of x, y inside C squared such that x, y is equal 1, right? This is, we had that already several times. Okay, then multiplication takes x, y inside this C star, which we consider as a subset in C2. X1, y1, you multiply by x2, y2, and you obtain the pair x1, x2, and y1, y2. Clearly, it also satisfies this condition, so it's a good multiplication. In fact, how we represent y, it's just x minus 1. So this is precisely the multiplication you have on C star. And then inverse, you have x, y, this is mu, and this is xy goes to yx. Clearly, if you multiply xy by yx, you will obtain 1 because 1, 1. So this is the unit of your group. Okay, this is an example of algebraic group, right? Let's do another example, which I also, not that I use it, but I will need it to define representations. This is just the group of matrices. In fact, it's not hard to prove that all algebraic groups are subgroups of matrices given by polynomial equations. So this means that what I'm giving to you now is the fundamental example, essentially the only example okay, over C, over number fields, it's probably not true. Anyway, so you have G which is equal to GL and C. This is a set of all matrices with determinant non-zero. Okay, so we removed a divisor from a set of matrices. So mat Cn is Cn squared. And this determinant equals 0 is a divisor, so how you represent it? The same way as we did here. So we represent G as a subset in matrices, which are already Cn squared times C. And it's a set of pairs. A inside matrices, T inside C, such that determinant of A times T is equal to 1. Clearly, this is the same as the set of invertible matrices. Now we need to do multiplication, but it is clear. Oh, first, this equation is polynomial because determinant is polynomial on the entries of the matrix. And then, if you want to multiply two matrices, you take A1, T1, multiplied by A2, T2, and you obtain A1, A2, T1, T2. This is the product of two matrices, and so T1 is determinant of A1 minus 1, T2 is determinant of A2 minus 2. The product of determinant of the product is product of determinants, so this is also an element of this set. So this defines you nice associative product. If, of course, we need to be able to invert matrices. So you take A, T, you apply this inversion operator and obtain something which is called adj of A and T minus 1. T minus 1. No, T. I think here I made an error. Yeah, it should be T here. Sorry. Where H is a matrix of A is what is called adjugate matrix. It's a matrix made from minors. So you take matrix, you remove an end, two a row and a column. You obtain a matrix n minus 1 by n minus 1. You take its determinant. This is called minor, and this is the matrix obtained from all minors called adjugate matrix. And the important thing that adjugate of A divided by determinant of A is A minus 1. This is how one defines the inverse matrix. Importantly enough, adjugate matrix is polynomial because it's many, many determinants. And T is also polynomial, so this is a good, well-defined polynomial expression. And here I made an error. I should have written T here and T there, yeah. So in fact, it's not T here determinant of A, because it should be inverse to the determinant of this matrix. Sorry, shouldn't forget to change this. Okay, we defined algebraic group structure on matrices. I mean, the multiplication we already knew. What we need to check is that it is expressed polynomially, and this is in construction of this polynomial expression. Okay. Zariski topology is something which we had. There's this example exercise that Zariski topology is the same as cofine topology. We already had that, I think, right? Yeah, what is important is what we didn't have last time is Zariski closure, or maybe we did, but now it's in the next slide in more detail. This is something I would use today. So if I have a subset, the Zariski closure is a minimal Zariski closed set containing this subset. So it's a minimal affine variety containing this subset. And then Zariski dense is something which is not contained in any proper variety. So if you have Z affine variety, you have A inside Z is Zariski dense. if a the Zariski closure, well, if any Zariski closed set containing A is Z. So the Z is the smallest Zariski closed set containing A. So there is an exercise that A inside C is Zariski dense if and only if A is infinite. Can you do that? Anyone? Can you do that? A is Zariski dense if and only if it is infinite.
It's because every proper algebraic subset of C is finite.
And conversely, every finite set is proper algebraic, right? Because if it has subset, it's zeros of the polynomial which has this subset as a root. And of course, if you have a polynomial, its set of roots is finite. So any algebraic subset is finite. Okay. Yeah, what is important, the following claim. Suppose you have A inside X, Zariski dense, and then you have phi from phi 1 from X to Y, phi 2 from X to Y are algebraic maps, and which are equal on A. Phi 1 is equal to phi 2 on A. Then phi 1 is equal to phi 2. There's even a proof. It's sort of easy. So the idea is that the set where two maps are equal is given by polynomial equations. Just the first map is polynomial, second map is polynomial. The phi 1 is equal to phi 2 is a polynomial equation on X. So it's Zariski closed. And if they are equal on A, this means that the set of points where it is equal is contained in Zariski closure of A. Well, contains Zariski closure of A, which means that it is everything because Zariski closure is everything. Clear? Okay, there's an exercise which doesn't have anything to do with Zariski closures. Well, mostly. Well, you can ask for polynomial maps as well, but still I think the easiest proof is just for differentiable maps. It's not obvious how you can use that is polynomial. Maybe we should discuss it. Exercise. You have a map from S1 to S1, differentiable, and homomorphism, group homomorphism. Then let's call it rho. Rho of t is t power d for some d, which depends on a rho. So depends and doesn't depend on t. So what do you think? Do you have any solution? Anyone? Okay, I can suggest a solution, which is, I think it's not optimal, but it is something. So it's differentiable. Yeah, let's compute its derivative. So d rho okay, so if you take a d rho, apply it to t1 plus t2, it will be equal to d a row of shifted by, so you have a row of T1, a D row in 0, plus a row of T2, D row in 0. This is just you use group law, and you use the derivative of the group multiplication is just 1. I mean, d of mu of x, y is x plus y. Okay. But this means the derivative is constant everywhere. So d rho by dt is constant. Just put T1 is equals 0, for instance. Okay. And then you have your rho is solution of the differential equation. Rho is solution of d by dt of rho is equal constant. So if you lift it to a cover, you consider it on R, this would be just linear function. And on, so it really multiplies. If you have rho of a point with angle alpha is some constant, d times alpha. But then d has to be integer because a rho of 2 pi is 0. So it can't be yeah. It cannot, d of course is integer. Okay, so this is a classification of homomorphisms from a circle to a circle. I suggest you to invent your own proof.
And it's not for just continuous homomorphisms, right?
No, no.
For continuous?
It's true only for continuous.
Yeah, for continuous, not only differential.
Yeah.
Can we reason it in this way? Just pick any irrational number.
Yes.
Which is not 1. It has like and it is sent to some, like by using the homomorphism property, it sends to some power of itself. But
Oh.
also
It's not sent to a power on itself, no. Why?
Okay, I just wanted to sort of to generate it, so to find the dense subset in this one.
Yeah, if you have an okay, but this is not a solution yet. No, I think you can do with continuity, yes, but it's not entirely. What is obvious that every homomorphism is determined by an image of continuous homomorphism is determined by an image of any rational angle, because just the group generated by one element is dense. I think the easiest way is to deduce from continuity that it is differentiable and then use this argument. But in fact, in the next slide, I have tried to prove without using this exercise and sort of failed. Well, there is a solution, but it's not. It has a complicated point. You will see it. And okay. Anyway, so what I wanted is, in fact, sort of similar theorem, but for C star. And then for any C star action on, what is the representation? There was a definition of representation here. I forgot to tell you, but it is obvious. So definition, algebraic representation. Algebraic representation is a homomorphism of G, of algebraic group G is a homomorphism G to GL of V, which is a morphism, which is an algebraic morphism. Algebraic morphism that is given by polynomial maps. You have coordinates on G where you have regular functions, and this map should be given by regular functions. This is actually why I needed GL to define GL as an algebraic group. Otherwise, we would somehow lose the category of algebraic groups. So what is the representation? It is a homomorphism to GL. Algebraic representation is algebraic homomorphism to GL. So it's a homomorphism of algebraic groups. Okay, now theorem. So this theorem is true for it was possible to prove it for continuous map, but it would be extremely complicated. It is true for differentiable maps, for completely differentiable maps. So you don't need algebraic, but the proof is also not. It takes some Lie algebras, at least. So I give you algebraic proof, algebraic theorem, and it's slightly easy. In fact, this theorem is true over any base field. You don't need C. And I try to do the proof which works over C, and sort of it has some tricky point which you can try to do yourself or just use that you have C. So any algebraic representation from rho from C star to GL of Cn is a direct sum. So when I say a representation is direct sum, I mean the space where the text is a direct sum. Is a direct sum of one-dimensional representations on each of V. So V is direct sum of Vi on each Vi. A rho acts by a rho of Z applied to V is Z power di of V, where di is integer, which of course depends on Vi, but doesn't depend on V or on Z. The statement clear? This is similar to what we have for fine groups. So probably the easiest way to prove it is to start with fine groups. And this sort of works. Oh, of course, you need algebraically closed field for that. Otherwise, it would be just false because you won't have direct sum. Even for rotations in R2, you don't have direct sum decomposition. So you really need algebraically closed. But that's all. This is true for any. Yeah, by the way, this group, C star, I erased it, but C star is denoted by GM in algebraic geometry. And we have, so proof step 1. So I will consider a final subgroup, GPN. Inside C star as a group of roots of unity of order p power n. This is a cyclic subgroup of order p power n. And then, as we have seen already, V is direct sum of Vi, where each Vi is GPN invariant and one-dimensional. Also, on one-dimensional space, automorphisms are C star. So a row from GPN to automorphisms of VI. So it's, I consider each VI as a representation, maps elements of this group to itself inside C star. Because it's automorphism of C star, but then they have order Pn, so it's roots of order Pn. Of course, it could be a non-trivial map because it takes some primitive root and puts it to some other root, probably primitive, but not necessary. Also, another problem is that as we increase n, the decomposition might be improved in the sense that you have, like you have here, you have roots of unity of order p, say p power k, and the same root of unity psi, and you have the same psi here. But then, as you go, as n increases, the corresponding root can somehow split. So as you go to infinity, your decomposition might change slightly, but very slightly, because, okay, this means that you have, once it split different way, you have to just go back and adjust the decomposition, and then it would work. So the decomposition makes sense, but what is not obvious is that we have this condition is slightly tricky. That it acts by a power of d, because, okay, it's a cyclic, so it really has, so for each, so step 2, for each n, this is an automorphism of cyclic group, so it is really for each n, a row restricted to Vi is a map. Z goes to Z power di of n. This because it's an automorphic cyclic group. I mean, any automorphic cyclic group where di of n is equal to di of n plus 1 modulo p power n, right? Because this g, because g p power n sits inside g p power n plus 1, this subgroup. So this just means that they're compatible. Okay, in fact, if you look carefully on that, you will see that this is just periodic numbers. But if you don't know periodic numbers, you shouldn't care. The important thing that you have like infinitely many digits, modulo Pn, where n increases, and they should be compatible. So if we don't have this condition of algebraicity or of continuity, you wouldn't have even you wouldn't have this statement even on this union of all groups of root of unity of order Pn. But the good thing is they're compatible, and so the union of all G Pn, the closure of this union is a circle. And our map is polynomial, so this and of course image of roots of unity is roots of unity, so row restricted to S1 to like S1 inside V endomorphisms of Vi is a map from S1 to S1. Okay, here I could invoke that we have algebraic maps. It has a finite degree. So this map, I use continuity here. I could avoid using continuity, saying that it has finite degree, and then this maps di cannot increase. Di cannot increase indefinitely because it has bounded degree. It's slightly tricky. So you can think of it and try to make it work, but I would just use that it is a map from C1 to C1, and it has by this exercise, so this map, a rho restricted to S1 is t goes to t power di. And that's it. Okay, now for step 3, I will use Zariski density. Step 3. Well, any infinite subset in C star is Zariski dense. In particular, S1 in C star is Zariski dense. And we know that rho is equal to degree map. Rho of z is equal to z power di is true on S1, then it is true on C star. That's it. Okay, so we proved what we wanted. We proved that really you have this direct sum decomposition for each representation of C star, and then on each summand it acts by taking powers. Okay. Now I'm going to tell you the important results about its important trivial result. But it really simplifies the thinking. And the idea is that graded spaces are the same as spaces with C star action. Of course, what I did give you now is a result about finite dimensional spaces. And typically, you work with polynomials which are infinite dimensional. So you have to do something to make it work, to work with finite type. Representations of finite type, definition. Representation of C star of finite type is a direct sum of Vi, where each Vi is finite dimensional, and on each Vi, our C star acts with the weight. By the way, this thing is called weight. On each Vi, rho acts by rho of z is z power I, where I, so I belongs to integers. I is called weight of C star action. This is an important word. I forgot to tell it on the slides, but you really have to use it. It's quite simplifies everything. Okay. This was the finite type grading. So finite type representations. So it's direct sum of representation, but each what is called isotypical component, the component of the same representation type, is finite dimensional. Now, graded vector space is something which we had already seen. So graded vector space is a V, which is direct sum of I belongs to Z. It's of finite type if all Vi are finite-dimensional. And morphisms. So morphism of representation is a map, linear map, which commutes with the action of the group. Morphisms of graded spaces are linear maps preserving grading. So if you have a component of grading I, it has to go to component of the same grading. Now, claim 1, graded vector spaces of finite type are the same category. So there's an equivalence categorical of categories with C star representations of finite type. Okay, there's essentially nothing to prove here. So if you have a vector space of finite type, good. On each Vi, we shall define the row action by this formula. This gives you a functor from graded vector spaces to spaces with C star action. Okay, if you have a space with C star action, you just look at all vectors which satisfy this equation. Row of Z of V is Z power I of V, this eigenspace of the representation. So it's, and you have a direct sum decomposition as we have proven before. Now, if you have a morphism, that it has to preserve eigenspaces. If it commutes with the group action, it has to preserve eigenspaces of the group action, then, but these eigenspaces are precisely the graded components. So this claim is tautological, it's trivial. Clear? Questions, comments? For whom it is clear? Okay, it should be clear because again, so you have your row action, row of Z acts on the, this is, row of Z is an endomorphism of your space. You take the direct sum eigenvalue decomposition of this eigenspace, and this is precisely your grading decomposition. This is how you get back from the representations to grading, and from grading to representation, you just use this formula. On the Vi, a row acts of row of Z is Z power I. It takes a vector and multiplies by the Z power I. Okay, now we have, this is something which we already did, the graded rings, but now I can finally give you a nice definition of graded rings, I mean, functorial. Okay. And so the idea is that graded rings are the same as, it's precisely the same as rings with C star action. Of course, to make it really work, we have to avoid pathological representations. I mean, we work with algebraic things, right? So we have to do algebraic. So definition. Well, graded rings is graded ring is a ring. Is it A here? A star, which is direct sum of AI with AI times AJ belongs to AI plus J, and this is a graded vector space. Of course, the ring structure should be compatible with vector space structure, so it's actually an algebra. But if it's not vector space, you can do that with rings. It's the same. Okay, and it's finite type. If all AI are finite-dimensional. Okay, So examples, polynomial rings. This is something which we have already done. So for polynomial rings, the degree, the homogeneous component of degree D is the eigenspace of your group action. No more chalk. Okay. Now we can also define group. I'm going to tell you why the rings with C star action are the same as vector as graded rings. So ring. So definition are a ring with C star action of finite type if R the representation of finite type. This means that it's the direct sum of finite dimensional representation of this type. Finally, and then you have to assume that rho of Z of AB is rho of Z of A times rho of Z of B. So this, maybe I should put extra brackets here, because here it means that I apply rho of Z. Z is an element in C star. I apply rho of Z to B. And here it means that I apply rho of Z to A, and here I apply rho of Z to AB. Okay. Now again, the same. Now it's proposition. Graded. So you have categorical equivalence of categories. Graded rings of finite type is the same as rings with C star action of finite type. Okay, so this sort of, I think this simplifies slightly this notion of, this explains why we have this. So why it is so, okay, you have, so if you have a graded ring, you have C star action. If you have C star action, you have grading. This is by claim 1, which I was on the previous slide. So grading on A is the same as C star action. So now we need to check that compatibility with multiplication means precisely this. So if you have V belongs to AI, W belongs to AJ, then the rho of Z of V W is equal to Z power I plus J. I'm assuming that this is a graded ring. This times VW. This is because VW belongs to, because VW belongs to AI plus J. This is precisely that. Conversely, if you have this, if this is true, then VW belongs to AI plus J. So compatibility with C star action is precisely the same as, now I have to make a break, sorry, until 1438. So you have 5 minutes. And you can ask questions, of course. Are varieties which are given. In the beginning, I defined you the projective space. Now we have projective space is a space of lines in Cn plus 1. But every time you have a homogeneous polynomial, it vanishes. If it vanishes on a point, it vanishes on the whole line because it's homogeneous. So every homogeneous polynomial defines zeros of homogeneous polynomials, or a system of homogeneous equations defines you a subset in a Pn. And this is what is called projective variety. Projective variety is a subset of Pn, Cpn, projective space defined by homogeneous equations, by a system of homogeneous equations. Okay. Homogeneous equations are given by a graded ideal. So definition, a graded ideal in polynomials or in graded rings, in A star graded ring is I star, which is direct sum of ik, where ik are graded. Ik belongs to ak. Of course, not all ideals are graded, but all ideals given by homogeneous equations are graded. So in fact, of course, the zeros depend only on the ideal. This means that you don't really use equations, you use graded ideals. So the projective variety, sorry, not manifold, variety is given by a graded ideal. Okay, now we have a C-star action. So this is convention which I will use, standard, or by homotopes. C-star action on Cn plus 1 is V, rho of Z of V is equal to ZV. It's homotopy, just radial expansion. Okay, now theorem 1. So you have this C-star action, and you have C invariance of variety. C-star invariant subvarieties are given in Cn plus 1 are given by great ideals. Conversely, each graded ideal, and it has theorem, it has a name, theorem 1, graded ideal gives C-star invariant subvariety. Okay, this is because graded is the same as C-star invariant, as we have just discussed. So proof. So what does it mean that it is so you have two categories. You have category of rings, you have categories of rings with C-star action. And the ideals in the second category are precisely the graded ideals. So a subspace, you have I inside your ring A star, which is just polynomials, O, C, n plus 1, is graded if and only if I star is C-star invariant. This is because we have equivalence of categories. Graded subspaces are the same as invariant subspaces under C-star action. And then, of course, the subset by Hilbert-Nullstellensatz defines you the ideal uniquely. So if you have an invariant subset, it defines you invariant ideal. Clear? Good. Now I can finish giving you Hilbert Nullstellensatz in that projective setup. It's not the whole Nullstellensatz because it doesn't give you equivalence of categories. It just gives you that certain objects can be defined. It's like you have a bijection between ideals and subvarieties. Well, radical ideals and subvarieties. Now you have bijection between radical ideals and projective varieties. Let's start with radical. So this is something you probably know, the terminology you know. As a definition, I inside R is radical if R quotient by I has no nilpotence, equivalently, if for each Z not in I, Z power D is not in I for each D. And Hilbert Nullstellensatz, I remind you, says that subvarieties in Cn are the same as C star invariant. Oh, sorry. Subvarieties in Cn are same as radical ideals I inside the ring of regular functions, polynomial functions, right? This is a bijection. So this is one-to-one correspondence between this set of all subvarieties and set of all radical ideals. I will prove you the same for projective varieties. But the main idea is that this gives you an interpretation of projective varieties as invariant subsets. So, so we can be interested. I mean, by definition, projective variety is variety defined by, in projective space, defined by homogeneous equations. So the Hilbert Nullstellensatz gives that you have a bijection, non-empty. In fact, here we really should say non-empty. Non-empty. Because if you remember the correspondence, it gives you, from a variety, the set of all functions which vanish in that variety. And for empty set, it will be everything. And we have a convention that ideal can't contain unity. So you have non-empty here. But then you don't really need to have non-empty because, well, you shall see. Projective varieties in CPN, subvarieties, are in one-to-one correspondence, bijective correspondence, with a radical C star invariant ideals, and the same as graded ideals, of course, in OCN plus 1. So this is like Hilbert Nullstellensatz, but for projective varieties. Very similar. Is the statement clear? So the idea is that, in fact, there is a third term which corresponds to that, one-to-one correspondence, with subvarieties, C star invariant subvarieties, in Cn plus 1 containing 0. So here you really have this non-empty to be applied. And how you prove this? You essentially prove that both of the sets correspond to C-star invariance of varieties. So there's three guys. These C-star invariance of varieties sit in the middle, and they are in bijective correspondence with both. Okay. So let's prove it. So we'll start with radical ideal. So zero set Hilbert Nullstellensatz for each radical ideal I. You take its zero set V of I. You take annihilator of this zero set. This is the set of all regular functions vanishings in there, and this is I. Now we have theorem 1, which I didn't erase yet. Theorem 1, which says that V of I is C-star invariant if and only if I is graded. Okay, now you have the set, take set Z. Z in, here it is, yeah, Cn plus 1. Or Z star, Z hat, inside Cn plus 1. It is Z hat is V of I. This is an invariant set. If you start with something invariant, this is invariant. Then for each point x inside Z hat, the line, the corresponding line generated by x belongs to Z hat. Right? Because it's invariant and the line is an orbit of C star action. This means that now first, so you start with projective variety, and this Z hat uniquely determines. So you take Z hat without 0. It will be Z, where Z inside quotient by C star, sorry. This is Z, where Z in CPN is subset defined by I. I is a graded ideal. It has zeros. Its zero set is just the set of lines which pass through the points of Z hat. This is clear. Okay. And so this means that Z hat, then Z hat is uniquely determined and determines Z. So if you have a projective subvariety, you consider its ideal, and you take the zeros of this ideal in the corresponding vector space. This will be Z hat. If you start with Z hat, you consider its vanishing, the annihilator, the set of all functions where it is vanishes. And it gives you a graded ideal, and this graded ideal defines you the Z. So in the end, you obtain a bijective correspondence between three set of data. So bijective correspondence. So the first is subvarieties in subsets in CPN, which are defined by graded ideals. So projective subvarieties. Projective subvarieties. In CPN. Okay. The second equivalent equinumerate is non-empty C star invariant subvarieties in C. Non-empty because when you do Hilbert Nullstellensatz, you have your ideal can be everything. So you can't have empty sets. So this is the same as non-empty C star invariant subvarieties. You have also, even if this is empty, you have to add 0 here. Subvarieties in C n plus 1. And the third notion, which is equivalent, is graded ideals, radical graded ideals. Okay, so the equivalence between these two guys comes because graded, it's theorem 1. So this is theorem 1. Graded ideals is the same as C star invariant sets. And the equivalence between this and this is Hilbert, more or less Hilbert Nullstellensatz. So if you have projective subvariety, it is defined by a graded ideal. It defines this guy, but then you can recover your subvariety from that just as a set of lines. Okay, I'm done for today. So next time I will tell you about the category of projective. Because so far we didn't have anything categorical. We didn't define even projective morphism. By the way, we have like 4 minutes. Can you guess what is a projective morphism of projective varieties? So you have objects of your category. What will be the morphisms? Yes. This is actually how mathematician works. He looks at objects, okay, what can we define with this object? How can we work it in a natural way? What category lives with this set of data? So this is really, so most time you don't solve problems. Well, you solve problems, but most time you just try to guess what is the natural setup for the problems which you can then solve. So this is the, I'm asking for a setup. What kind of category you can define together with the with this geometric datum? Yeah. The problem is that homogeneous polynomials are not defined as functions on your varieties. So it's not clear how you can use them to define maps.
But we got affine charts on.
Yeah, but they're not defined on affine charts either, because they're defined up to a multiplication by a function. if I were you, I would guess that, okay, we know that projective varieties are the same as C-star invariant affine varieties. We know what is morphism of affine varieties. Let's define projective morphism as C-star invariant morphism of affine varieties. Doesn't work. For some reason, this is bad, and the correct notion is non-natural, but this is how it works in nature, that you have, so you have your x with C-star action. You have y with C-star action. You have a morphism, and then it have to commute with C-star action, but not quite. But on C-star, it have to go like z goes to z power n. Then it works. So if you have here zx, as usual, on the image, it has to act by z power goes to z power n. And the main idea is the following. So the set of coordinates which you get from CPN is not, it's a set of coordinates, and you want to get to be coordinate free. And the best way to be coordinate free is to replace your ring of functions. Say you have the ring of functions, the homogeneous polynomials, by homogeneous polynomials of degree, homogeneous polynomials of degree k power d, where d is fixed. This is also a homogeneous ring. And homogeneous rings are really what you, and it would define you the same functions. It's not hard to see that. Okay, next time we shall discuss that more. And today I'm finished. Thank you very much. And hope to see you next Friday.